right? Because that's the whole point, is to make things easier, to get stuff to work for us. And so in order to get things to work for us, Benjamin Franklin started writing about batteries and current, and they started making batteries and storing up power for times that you don't have power. Okay? Because if you have solar energy to heat something, it's great when the sun's out. It's just not real great at 9 o'clock at night, right? So they needed to find a way to start storing this power. And we did it with batteries. So we can store the power in batteries. We know that our energy comes from the movement of electrons. So if we were to look at a battery and we were going to put all of our little particles inside of it, okay, we've got a whole bunch of electrons. So they're all negative. So they want to get out of here, right? Because if you have a bunch of things that are negative, what did we learn last week? Like charges repel and opposite charges attract. So we have a whole bunch of repelling items in here, right? So they're going to want to try to escape. But since our systems, like Dave mentioned earlier, it's neither created nor destroyed. If it goes somewhere, then you're left with a void. And voids like to suck things up and be filled up. And we have a positive charge over here on the end. And so now we have negative ones that are floating out in space. They've been expelled from the end. And now we have opposite charges. So they're being attracted over here onto the positive side. Okay? So we have this battery. It's now storing this energy, and it is automatically causing a desire for movement from the inside. Simply because like charges repel and opposite charges attract. And so we're going to end up with, as it moves through, I've got a whole bunch of, I've got this space. And often batteries, if you break them up, they'll have some type of membrane in the middle. So I've got this space where they're all charged up, they're all the same. I want to get rid of it. I've got my opposite charge over here. I want to get to that. I want to be different, and so it's going to transfer through that. So with batteries comes two terms that we needed to know. We have voltage and we have amps. Okay? And when we talk about both, it seems to be that they're talking about the same amount of stuff. But I'm going to use a baseball analogy here. If I had one baseball and I just hit it to you, if we're going to relate, I would have 1 volt and it would fly at you at a certain speed. Now, if I still have that same one baseball and I have Ty Cobb hit it to you, it's coming at you a lot faster than me hitting it to you. Correct? Or my favorite, Chipper Jones, old school. And so, again, we would have the same item, but it is going faster past a point. And so it might cause more damage. Now, if I had 5 baseballs and we hit with Miss Thomas strength and they hit all at one point, it might cause some damage, definitely more damage than the 1 baseball, simply because there's more of them, correct? Now, if we hit all 5 of those and Chipper Jones hits them all, we're causing significant amount of damage. So that is the difference between our voltage and our amps. Voltage is the amount of push that you can actually have towards something. Okay? So if we have a 9-volt battery, it's going to push with 9. We'll just do that number, 9 for it. So if you have, a circuit and you have something, or if you have a car battery, which is typically 12 volts, it's got more push through it just because it's 12. So as you have a bigger voltage, it means you've got some more strength. You have more of the amount that are coming through it. So the first one you might have like 9 baseballs coming, then the second one you've got 12 baseballs coming. You've got more items that can be moved. When we're talking about amps Amps is how much is passing through a certain point at a certain amount of time. This is like your speed of what's moving through. Okay? So if you have one thing going slowly through this point, it's probably not going to cause much damage. If you have one thing going fast through this point, it's going to cause more damage, right? It has more power for it. If I take 5 things and I move slowly through the point, I've still got some significant amount of damage. If I take 5 things and I move them really fast through this point, now I've got tremendous amount of damage through it. So our volts and our amps work together to tell us how much energy or amount of work that like battery or that item that has stored it can do. Okay, so if you have a high voltage but not very low, you got a lower amps, in the book it says the only safe thing is low volts and low amps. Okay? So as soon as, if we've got volts and amps and they work together, as soon as we have one goes up, then the whole system has gone up, right? So if I have high volts, even if I have low amps, do I still have a dangerous system? Yes. Now, if I have high volts and high amps, we're exponentially more dangerous than that. And so in your house, there's different types of amps. You might have appliances that take 120. You might see that. You might have 220. 120 and 240. So what would you say would be the difference between 120 and 240? Is one double the other? What one's going to be more dangerous?
240.
240. 240 is going to be more dangerous as far as power goes, like the actual amount that comes to it. An anatomy lesson is 120 is actually more dangerous to you physiologically because it's closer to your heart rate, to your biomechanics for it. So it interferes with your biological systems more severely than 220. That's an interesting side fact for it, okay? So as we have our volt and our amps, the whole part of it is with our current. And so they say in your book that our current is the amount of charge that travels past 1 point each second. So we are actually putting a quantity on that point, and that is going to be our current amount that we have pushed through. So how does our current move in the first place? What's great is Benjamin Franklin came up with a bunch of different symbols and started drawing things because does anyone have a dad that's an architect or a parent that's a architect or an electrician or anything? Okay. So when you're doing building plans or lots of big plans, it's easier to write things in symbols. You know, if you're an architect and they show, oh, there is a door that goes here, or here's a window right here, because you're looking on a flat surface of what's happening. So with electrical currents, as we are drawing circuits, we get to do the same thing. And so they have this great chart here on 411, which is super fun to look at. You can draw all different types of circuits with it, but it gives those 2D versions of something that you would see in a real life version. So if you wanted to talk about it being a wall switch or a light that's on the wall, or whether it's something, maybe it's a ceiling fan that's hanging that needs some electricity, you would be able to know by looking at the paper exactly what they're wanting to put in all of those different places. Okay? So as we have our battery, a battery in a circuit is drawn as one long side and one short side. Kind of looks like the battery for it, okay? The long side is the positive side. The short side is the negative side. I like to think of it as I like more positive things than I do negative things. If that's a easy mind trick to help you remember which side is what, okay? So Benjamin Franklin said, well, of course we always go positive and negative, right? I mean, whenever you're writing an equation, you're going to write the positive number first. So he drew circuits going from the positive to the negative side, and that is called conventional current. If someone says, oh, you're being too conventional, we could also replace the term conventional with like old school. You're doing it the old school way. Like there's a new way to do it in town, but you just keep doing it the conventional way. So conventional current means we keep drawing it like this, even though it's not right. But there's way too many documents that would have to get changed to change this. What do we know about electrons? What charge do electrons have?
Negative.
A negative charge. So which side of this battery would they want to get away from? The negative. Because they have a negative charge, they want to get away from the negative side first. So instead of them coming towards the negative side, our current truly comes out of the negative side and it goes into the positive side. Okay? So as current is flowing, it matters what it flows through. We know that it always wants to flow. It's going to go from one place to the next. It's never created or destroyed, so it ends up going somewhere. There's two different types of things that current can go through. It can go through a conductor, or it can go through an insulator. A conductor does exactly what it says. Conducts. A train conductor takes the train from one end to the next. Correct? So conductor metals take our electrons from one side to the next, and it moves it through. An insulator, if you were to be insulated inside something, it means that you're not going from one to the next. We want to, in Oklahoma, be insulated from tornadoes, correct? So we put something between ourselves and the outside so that it can't transfer from one to the next. So conductor metals or conductor items, water is an excellent conductor, and it's not a metal. Okay? So anything that's in conductor means that it's going to easily take our power from, or our movement of our electrons, it's going to move them from one side to the next very easily. They are quickly going to be able to pass through. We're going to have that going. So if you think about fiber optics now, or the power lines that are overhead, the metal or the what is used, whatever they choose to use a metal that they use in there is going to matter, correct? Because they're wanting to get power all the way from the power station out on Route 66 all the way into Edmond or Arcadia or Luther or whatever else. They're wanting it to travel. So we're not going to want to insulate. So there are certain conductors that help go through fast, and then there are insulators that break up that movement so that whenever it's moving along, it's saying, no, I'm not going to be able to go that fast. Styrofoam is a great insulator. There's some plastics. Fabric doesn't allow electricity to move through it very quickly. Because water is an excellent conductor, would your body be an excellent conductor? I see head shaking. Why do you think your body would be an excellent conductor?
It's mostly water.
Because it's mostly water. Correct. That is why it is important that we're safe as a human around electricity, because we are excellent conductors because we're made up of a lot of water. Okay? And because, I'm going to give you an extra tidbit that's not in, because we have to complete a circuit, and we're going to talk about open circuits and closed circuits. Because we have to complete a circuit, when there is a break in the circuit, okay, the danger comes in a completed circuit. That's when it actually lights something up, if we have a light bulb on it or something. So for cars, we have rubber tires, and electricians that will work in rubber boots because rubber is an insulator. What it's doing is, you've heard the term grounding. It's breaking that circuit. So if you could really see, their body is accepting, they might actually get shocked. They're accepting a charge and it's going through. It just doesn't have anywhere to ground out. And so it's not causing any damage with that. All right? So if we were to send all of our electrons here through some type of metal or some type of device, we're sending it through. We've got a bunch of electrons that are shooting through. What's going to happen when these electrons meet these atoms over here? Is there a chance for them to collide? Yeah, there's a chance for them to collide. And if I say maybe there's 8, I'm just going to pick 8 little atoms here, and I stick all 8 of my atoms in this tiny, skinny space, what are the chances of my electrons colliding with something?
More.
It's a lot higher, right? Because it's a smaller space. There's more stuff packed into it. If I take them and I spread them out into a larger space, what's the chance of them colliding?
Less.
It's less than. So resistance is the impediment of our electrons as it moves through something, whether it's moving through a conductor or whether it's trying to move through an insulator. We have this resistance, okay? If it's in a smaller space, so a thinner wire, then it's going to have a lot more resistance. A thinner wire or even a longer wire. They talk about length having to deal with resistance, right? Because if I'm going from point A to B on my short wire, I only have to collide with X number of particles. But if I'm trying to get from A to C down here, I've got 3 times as many that I have to get through. It's like a real bad obstacle course. You know, the longer it is, the more obstacle is, the more chance that you have of running into something, correct? For it. So we're going to have more resistance if we have something longer or if we have a tighter packed space, which is going to be like a small wire on that. So when it looks at wires, they will talk about them being thin wires or thick wires. They'll talk about them being short, and you read about them being long also. Okay. Resistance, when we learned this way back at the beginning, when we have one object run into another object, what occurs between them?
Friction.
Friction. Friction produces heat every single time. So this is where we get our heat. And so this is how we get to use all of the things that we learned way back at the beginning, even things about friction, to create items like old school electric stoves have your heating coil on the middle. Okay. You want this heating coil to get hot. So are you going to make this coil out of a metal that easily passes electricity through it? No. You want the electricity to actually pass through it in some way, but you want there to be some resistance because you want to produce heat out of it. So they're going to make it out of a metal that's going to allow enough passage so that we actually make it all the way to the end. Correct? So it needs to conduct enough to at least make it through. However, resisted enough that it's going to put off some heat, that there's going to be friction every time that that's moving through. And we're going to have some resistance there. I was trying to think. I might need to do a test. Okay. So quickly on circuits, and then we're going to get to our fun lab. When we have circuits, and we have them drawn. A circuit means a complete loop. When there is a complete loop, it is called a closed circuit, which makes sense because all the parts are closed on it. If there is an open part, it is called an open circuit or a broken circuit. So if I have a little light bulb over here, okay, and my electrons are leaving, we'll draw it conventionally, it will not turn on unless we can close it all the way around. There has to be a complete path for those electrons to do any work to complete something. So when we have an open circuit, anything along the path is not going to work. When we have items in parallel, they use the word, in series. Okay, series in math, when you talk about series, it's numbers in a row is a series. Numbers added up in a row. So we're adding a bunch of things on the same row. Okay? So if I have a series and I have a bunch on the same row, if one goes out, it affects everybody. Correct? Because it works just like an open switch. And you can't complete your loop. So they came up with a way, and this is how old school Christmas lights used to work, which is, if you have as many Christmas lights as we have, it's annoying. So when one bulb goes out, then all of them go out. Then you have to figure out which one is out to replace it. Okay. So a way to get around that is to detour. We all love detours. You come to a road. I drove down Coffee Creek the other day and realized that it is closed at Air Depot. Did not realize that it was closed there. It said open trench. I didn't want to try to risk it past that point. But there was a big detour sign. So I couldn't go there. So I drove up 1 mile, went over, and went around. When we set a circuit in parallel circuits, there gets to be a detour. So if one part of it goes out, it doesn't affect the other part. There's still a way, as long as there is still a way to get from the start back to the beginning. It's like a complicated maze. All we're doing is trying to find a way to get back from the beginning. So as we work, one of the goals today on your labs is to create a parallel circuit so that we can take one bulb out and the other bulb is going to stay lit. And so to work through, where do the wires need to go? If I have to start at the beginning and I've got to work through 2 separate ones, how can I set that up? There are examples that we are going to follow through, but for a couple of them, I'm going to ask you to try to figure it out on your own, and then we'll hand you the instruction guide on it, okay? So that is all that we needed to know for your test, because you guys are finished up, and then you'll take your test and give that back to me after spring break. You need to know about volts and amps, that if one goes up, it makes the whole circuit more dangerous. So we only have safe circuits if we have low volts and low amps for it, and that our current is the amount of energy that we have moving through that one point at one time. All right, so let's do, oh good, we only have 6. Perfect, because Bella didn't come. So let's just do tables and I'll pair you guys up. Dane, go with Katie.